Welcome to the lesson on how geometric tolerancing is superior to coordinate tolerancing. Did you know that coordinate tolerancing is outdated and should only be used in limited places on drawings? This lesson is important because it explains the shortcomings of coordinate tolerances and shows how geometric tolerancing eliminates these shortcomings. Your goal for this lesson is to understand why geometric tolerancing is superior to coordinate tolerancing. It's important for you to know these terms in order to understand the two dimensioning methods being compared. For about 150 years, a tolerancing approach called coordinate tolerancing was the predominant tolerancing method used on engineering drawings. Coordinate tolerancing is a dimensioning system where a part feature is located or defined by means of rectangular dimensions with given tolerances. Although the coordinate tolerancing method is inadequate to communicate many design requirements for engineering drawings today, it's still used on many drawings. Coordinate tolerancing does a good job defining sizes of holes and pins, but does a poor job locating or orienting holes, diameters, and surfaces. Coordinate tolerancing leaves out several important pieces of information about how to inspect a part. It also increases costs and causes safety or functional problems. An easy way for you to remember the shortcomings of coordinate tolerancing is to think of the word unsafe, which will remind you that parts dimensioned with coordinate tolerancing can result in functional or unsafe conditions for the customer. Each letter of unsafe relates to one of coordinate tolerancing's shortcomings. Results in ambiguous instructions for inspection. This figure shows two logical methods you could use to set up the part for inspecting the holes. You could rest the part on the face first, long side second, and the short side third, or on the face first, the short side second, and the long side third. Because there are different ways to hold the part for inspection, you and another inspector could get different measurements from the same part. This could result in two problems. You could reject good parts, or worse yet, you could accept bad parts as good ones. No indication of measurement origin. If you take a measurement from a reference plane, the form error of the surface is not part of the measurement result. If you take a measurement from a surface, the form error of the surface will affect the measurement result. Each measurement provides a different answer. Since this is not covered in any standard, there's no way for you to determine which measurement is correct. Square or rectangular tolerance zones. Since coordinate tolerances use a tolerance in the y or vertical direction and a tolerance in the x horizontal direction, the resulting tolerance zone is square or rectangular. The tolerance zone for the hole location is formed by the max and min of the x and y location dimensions. Accumulation of tolerances. Coordinate tolerancing can result in tolerance accumulation. In this figure, the total deviation in the vertical direction for the lower hole is 0.5. The allowable deviation in the vertical direction for the top hole is 1.5 because it includes the tolerance accumulation from the lower two holes. Where coordinate dimensioning includes the use of chain dimensions, the tolerances from each dimension in the chain accumulate. The tolerance accumulation can cause problems for the function of the workpiece. Fixed size tolerance zones. Coordinate tolerancing uses fixed size tolerance zones. The drawing specification requires the center of the hole to be within a 0.5 square tolerance zone, whether the hole is at its smallest or its largest size limit. When the important function of the holes is assembly, the hole location is the most critical when the hole is at its minimum limit of size. If the actual hole size is larger than its minimum size limit, its location tolerance can be correspondingly larger without affecting the part function. This is a result of the additional clearance between the mating part and larger hole. Coordinate tolerances do not allow the tolerance zone to increase in size as the hole size increases. Exact start point of dimension undefined. A coordinate tolerance uses a double-ended dimension line. It does not indicate which end of the dimension is the start point and which is the end point. There are many instances where measuring from one surface or the other results in different measurements. Measuring from one surface or the other also affects the orientation of the measurement, which can make a difference as to whether or not a dimension is within the drawing specification.
To continue.
When the location or orientation of diameters, widths, and surfaces are dimensioned with coordinate tolerances, there are several ways you can interpret the dimensions for inspection. This can result in several undesirable conditions, including increased manufacturing costs. This is often noticeable as the scrap and rework required when coordinate tolerances are interpreted differently between production and inspection. Part acceptance disputes. Customer and supplier disputes are expensive and time-consuming. These disputes can ruin necessary trust of business relationships. Build problems. These are embarrassing and expensive. These often result from not understanding design intent or the true interpretation of a dimensional requirement. The consequences of using coordinate tolerances are related to applications where coordinate tolerances are applied but cannot provide a single clear interpretation. Not all applications are poor applications for coordinate tolerances. However, you should only use coordinate tolerances to define size dimensions, non-critical chamfers, and tangent radii.